All right, I think it's time to get it started. Welcome back. We do have homework due tomorrow, as usual. I hope you've had a chance to check it out. We're talking about limits at infinity. That's what we started discussing last time. Also known as horizontal asymptotes. Horizontotes, as I wrote there. Limits at infinity. This is like something like lim x goes to infinity of 1 over x is 0, right? That's a true fact because this would be a fraction in which the denominator is becoming infinitely big, and the value of that fraction, as the denominator continues to increase, will approach 0, right? Limits at infinity. This also represents a horizontal asymptote of that function, 1 over x. You know, the graph of 1 over x looks like this. And this particular limit, as x goes to infinity, is expressing the fact that as you go off to the right, the graph approaches this horizontal line at y equals 0. All right, so that's the connection between horizontal asymptotes and limits at infinity. They're actually the same thing. When I say limit as x goes to infinity, I'm talking about a horizontal asymptote as you go off the picture to the right side. And we can also do limit as x goes to minus infinity, which would be the horizontal asymptote as you go off to the left side. And in this example, they're the same, although it's not necessarily true. They're not always the same. All right, limits at infinity. So I think we finished off last time. I told you a very basic fact about limits at infinity, and it was this. The lim of any constant over any power of x is going to be 0. When x goes to infinity for any constant k and any other constant r, which is greater than 0. If r is negative, then this is no longer true. The whole reason that this limit is 0 is because the r is in the denominator, which means I have a fraction here where the denominator is becoming infinitely large. If the r was negative, then this would actually flip back into the numerator, and then it wouldn't be the same situation anymore. And then the same is true when x is going to negative infinity also. So this is x going to minus infinity. Although this time you're not allowed to have fractions in the exponent because a negative number to a fractional exponent is not always a real number. Like negative 1 to the 1/2 is an imaginary number. So this is for any k and r, an integer, a positive integer. And I think that was the last thing I wrote last time. A positive integer. Right? This is a very, very basic limit as x goes to infinity. What I want to talk about today is more complicated. How can you figure out more complicated things and what their limit as x goes to infinity ends up being, right? There's a standard trick, which maybe you saw this in high school, for more complicated things. More complicated functions, still involving powers of x, but maybe involving also fractions and radicals. For more complicated functions, I'll say, I meant to insert, can I insert a word there? Sorry. Algebraic functions. I said this word maybe way back at the beginning of the class. An algebraic function is one which is just it's like polynomials, but also combined with radicals and maybe fractions in it. So an algebraic function can be written as a big fraction, where the things inside the fraction are either polynomial type things, or they have maybe square roots in them, all right? So for complicated algebraic functions, there's a basic trick here. I'm going to say there's a fancy trick. I just said it was basic. Kind of fancy, too. The trick is divide everything by biggest power of x. Maybe you've seen this before. we'll just do, so it's not very fancy as far as tricks goes. It's fairly easy with simple examples, but this can get, there's like some subtleties to it, which can get kind of complicated. So we'll start with the easy ones. How about, can we do lim x goes to infinity of, let's say 3x squared minus 7x plus 5 over 4x squared plus x plus 1, all right? And the trick, like I said, is divide everything by the biggest power of x. So you want to look everywhere here on the top and the bottom. What's the biggest power of x that you see anywhere? And I see x squared is the biggest power of x that I see anywhere. So I'm going to divide everything on the top and the bottom. I say divide all by x squared. Since we're doing the same thing on the top and the bottom, dividing on the top and the bottom, it's not going to change the fraction. This is just another way of writing the same thing. So we get lim x goes to infinity. All right, so 3x squared becomes 3x squared over x squared, and then minus 7x over x squared, plus 5 over x squared. I'm just dividing everything out by x squared on the top and on the bottom. 4x squared over x squared, plus x over x squared, plus 1 over x squared, right? Once you've done this enough times, you can skip some steps here. Next, I'm going to just simplify everything. The 3x squared over x squared, those guys can cancel, and these guys can cancel, right? The x squareds. In the other ones, there's going to be some x's kind of left over, but anyway, it's lim x goes to infinity. It's going to be up top 3 minus 7 over x plus 5 over x squared, right? And on the bottom, 4 plus. I'm going to cancel x over x squared, cancels to 1 over x, and then plus 1 over x squared. Okay? I canceled as much as I could. But now, what was the point of that whole trick? The point of that trick happens right now. At this point, we can do this limit everywhere inside the fractionary. The 3 and the 4 are just going to stay like they are, but everything else here will become a 0 when you take this limit, because they are all some constant divided by power of x, which is what we said right up here. These limits always equal 0. So I'm going to actually do the limit here, and all 4 of these guys here, they all become 0 because of that basic principle that I said at the beginning. So all we get is 3 minus, I'll just write it out, 0 plus 0 over 4 plus 0 plus 0. Anyway, 3/4 is the answer. So the limit of that thing as x goes to infinity is 3/4. You could think of this as just an abstract, made-up problem. Find the limit. This also represents, like graphically speaking, it means this function, if you were to graph it, it has a horizontal asymptote going to the right, because x is going to infinity. It has a horizontal asymptote at y equals 3/4. Right? That's the graphical interpretation of what that means. All right? Any thoughts about that? This was an easy example, and nothing really fancy will happen. What if instead of x going to infinity, this was x going to minus infinity? Actually, you would get the same answer, because the only time when we did the limit was in this step right here. This is when we actually did the limit. And what if the limit was going to minus infinity instead? These things, they still all would have become 0. So can I just say, also, in this case, you would get the same answer if you went to minus infinity. So same function here, 3x squared minus 7x plus 5 over 4x squared plus x plus 1. This limit is also 3/4. All right? It doesn't matter in this example if it was a plus infinity or minus infinity. All right? That's the basic trick. There is a little subtlety involved when there are radicals. All right? So it gets a little fancier with radicals. More fancy. Let's just try an example. How about lim x goes to infinity, 5x to the 4 plus square root 2 plus 4x to the 10 over 6x to the 5 plus 7x squared minus 1. All right? Now, I said before, the basic trick is divide everything by the biggest power of x. In this case, just looking at it, the biggest power of x that I see is x to the 10. But because x to the 10 is inside the square root, it turns out actually you don't want to divide everything out by x to the 10. You want to divide instead by x to the 5, which is half of 10. And x to the 5 I also see down here. The moral of the story is x to the 10 inside a square root counts like x to the 5. All right, half of that. It's because the square root is like a 1/2 power. And so any powers that you see inside the square root, you have to consider them as really kind of half of what you see on the page. So that x to the 10, when I'm looking for the highest power of x, it doesn't actually count like an x to the 10. It counts like an x to the 5. And I also have x to the 5 on the bottom. So x to the 5 is the biggest power of x overall. So in this example, the biggest power, which I'll put in quotes, is x to the 5. All right? This is a little more subtle than what I suggested at the beginning. It's not always just whatever you see looks the biggest. You have to consider a little bit where it is. If it's inside of a root, you have to modify. Anyway, now that I know the biggest power is x to the 5, I'm going to proceed like we did before. So divide everything through by x to the power 5. So this limit here equals, then 5x to the 4 over x to the 5. Now something slightly weird is going to happen with this root. I'm going to just write it as 1 over x to the 5 times the whole root. 2 plus 4x to the 10. And then I get 6x to the 5 over x to the 5 plus 7x squared over x to the 5 minus 1 over x to the 5. Right? All of these little terms here with the x to the 5s in the bottom, we know how to handle them already. They will work just like we did before. What about this thing here? 1 over x to the 5 times this square root. My intention is to shove this thing inside the square root sign. Anybody recall how to do that? Can you just stick it in there? The answer is no, you can't quite just stick it in there. What should I do when I send it inside? I heard somebody whisper. I don't know what she whispered. What do you do when you move it inside the square root? Maybe she was whispering an unrelated thing. That's all right, I guess. This is kind of like maybe it's easier to remember it like the other way around. Anybody know something about what if I had a square root and it was like x to the 4 times 3 plus x. Can I move this outside? You can't just put it outside like x to the 4 times the square root of the earth. But what happens when you do that? Maybe you don't recall this. That's all right. This is multiplication here. Actually, a square root, you can just break it apart like this. And then this root of x to the 4 is x squared. You divide the exponent by 2. All right. The moral of the story here is when you bring something out of a square root, it can come out, but you have to divide its exponent in half. All right. And if it had any coefficients, you'd have to take their square roots. But when you move something out of a square root, you divide its power by in half. The other way around is when you move something into a square root, you've got to square it when you move it in. So this one here, 1 over x to the 5, when I push this into the square root, it becomes 1 over x to the 10. That is, you square the x to the 5 down there. So this stuff, I'm going to continue here. What? Delete. All right. I put that guy into the square root sign, but it becomes a 1 over x to the 10. So I still have this thing. All right, square root. Now it's 2 over x to the 10 plus 4x to the 10 over x to the 10. All right? I shove the 1 over x to the 5 into the square root. And when you do that, you've got to square it as it goes in, which in this case means x to the 5 becomes x to the 10. And on the bottom, same old stuff. And now we're ready to just sort of cancel stuff out in the same way as in the earlier easy version of this example. All right? So I'm going to cancel a bunch of things. 5x to the 4 over x to the 5 is just 5 over x, and then it's going to be plus square root 2 over x plus 4, that's just 4, right, over 6 plus 7 over x cubed minus 1 over x to the 5. Canceling by subtracting the exponents. And then now that this is simplified, we can take the limit as x goes to infinity, and like a lot of those things will turn into zeros, right? Anything which has x's left over in the denominator becomes a 0. And that 4 and the 6 will just stay as a 4 and a 6. So I get, 0 plus square root 0 plus 4 over 6 plus 0 minus 0. And this is root 4 over 6, which is 2 over 6, which is 1/3. And that's the answer. All right. That's how we do a slightly more complicated one. If it has a radical in it, when you're finding the biggest power, you have to modify your expectations or your judgment about what the biggest power is. All right. Any thoughts about that one? All right. That was a little weird. Actually, it's ever so slightly weirder than that. When you are making the x, sorry, I mixed up my pages here. So yeah, let me just say, we used, so the sort of basic fact that we just used, we used this fact. If you have x root y, this is equal to root of x squared y. When you bring something into the square root, it gets squared when you bring it in. So what, in the example we just did, it was a x to the 5, which became a x to the 10 when you bring it into the square root. That's how these things work. But it's ever so slightly more complicated than that. Actually, this is true only when x is positive. This is a weird but true fact. When x is negative, the rule is slightly different. X times root y will be negative. Remember, when you have, if the x, when I wrote when is negative, when x is negative, here, you're going to have x times the square root of y. Now, when you see this root y, the answer of a square root is always positive. Sometimes we have to insert a plus or minus, but when I just write a square root sign, that means the positive one. If x itself is negative, then this is negative because I'll have a negative times a positive. But if I move the thing in, x squared y, this is positive though, just because it's a root of something, right? And the square root sign indicates the positive square root, all right? So they cannot be equal, right? I said up here, when x is positive, those two things are actually equal. But when x is negative, they are not equal. In fact, they are opposites. So this is just a technicality rule you got to remember. When x is negative, actually x root y is equal to minus root x squared y, all right? So you have to just remember this little technicality. That trick where you shove something into the square root and it gets squared in there, you can always do that. It's just when the thing you're moving in is negative, you have to insert an extra negative sign. This is sad but true. Weird but true. Right? What does this have to do with anything? This often matters in lim x going to infinity versus lim x going to negative infinity. All right? If you are trying to do this thing where you move the x inside of a square root, if the x is going to infinity, you leave it as positive, but if the x is going to minus infinity, you have to insert this minus sign because the x is going to be negative when you move it in there. All right? Here's an example of what I'm trying to do. I'll try to write in words. This means, to summarize this little technicality. So in a lim x goes to infinity, you can do this. X root something equals root x squared something, right? But in lim x goes to minus infinity, it must be this way, right? If the x is going to minus infinity, that means the x is going to be negative, like super big negative. You have to insert that minus sign. And this basically is what, like I keep on saying, there are some examples when the limit to infinity is different from the limit to minus infinity. It's usually because of this weird little rule. When the x is going to minus infinity, it behaves differently with the radical signs. All right? So I got two examples of this, and then I have one for you all to try. How about this function, lim x goes to infinity of square root x squared plus 4 over x. I want to do this, and then I also want to do lim as x goes to negative infinity, the same thing. All right? Anyway, we, don't worry about what I just said until it comes time for it. When you see a problem like this, you want to divide out the top and the bottom by the highest power of x. What would you say the highest power of x is in this problem? The choices are 1 or 2. What do you say? You can show me the fingers if you like. I see some disagreements. I see some ambiguous, perhaps just finger stretching. I believe the answer is 1 in this case. I do see a 2 there, but remember what I said before. When you see a 2 that's inside of the square root sign, you only consider that as half of whatever you see. This is just like that example where we saw x to the 10. It was inside the square root, so it counted like an x to the 5. In this case, it's an x squared, but it's inside the square root, so it counts like an x to the 1. So the highest power of x here, in quotes, the highest power, is x to the 1. I'm going to divide by x to the 1 on the top and the bottom. It becomes lim x goes to infinity, 1 over x, root x squared plus 4, on the bottom, x over x. All right? And then I'm going to shove that 1 over x into the square root. It will become 1 over x squared when it moves in. And it multiplies, would you mind if I distributed on these two things? 1 over x squared times x squared, and also 1 over x squared times 4, right? And on the bottom, x over x, that's 1. You don't mind? All right, I shoved it into the square root sign. It became an x squared. I'm doing this rule right here, basically. And because x is going to infinity, in my example here, that means the x will be positive, and it means that step is legal. If the x were negative, I would have to insert an extra minus sign, but it's not. X is positive. All right, let's continue then. Simplify stuff. On the inside of the square root, the first thing is going to be a 1, and then it's going to be 4 over x squared. And then on the bottom, I have a 1. You take the limit, that 4 over x squared becomes 0, and whatever's left over is the answer. In this case, it's just square root of 1 over 1, which is 1. So the limit as x goes to infinity is 1. All right. Okay, I said I wanted to also do x going to minus infinity. Same function, but x going to minus infinity. Oh no, I need to do that. Okay, I got it back. Same function, though x going to minus infinity this time. What's the difference? The difference will occur right here. When you shove this thing under the square root sign, you have to insert an extra negative. That's because of this weird rule here. So I am going to do the same initial step, which is divide everything by x. X is going to minus infinity. All right, 1 over x square root, x squared plus 4 over x. And then, x over x, right? I divide everything by x. And then up top, I shove the 1 over x into the square root sign, and this creates a minus sign. This is the weird technicality. One weird technicality they don't tell you about in high school. I'm trying to think of a good clickbait title for this video. Your high school teacher doesn't want you to know. That's what it's got to be. 1 on the bottom. All right, and then, simplify in the same way, right? The same stuff is going to happen as happened in this first time around, only I have an extra minus sign right there. That's the whole point of this example, is that extra minus sign. All right, so I'm going to get, would you mind if I just skip to the limit? It's going to be like this, right? So the answer is minus 1. So this is an example in which it's the same function. I got 2 different limits as I go to plus infinity versus minus infinity, all right? And what this means, actually you can see this on the graph. If you graph this function, the first thing, the answer was plus 1. That's the horizontal asymptote as we leave the graph going to the right. I happen to know what the graph of this looks like. It has a, because of the division by x here, it has a vertical asymptote actually at 0. We learned that when you go to infinity off to the right, the answer is 1. So it has sort of a horizontal asymptote to the right at 1 and a horizontal asymptote to the left at minus 1. And the graph, if you graph this on your calculator or something, you'll see it looks like this. There's different limits as you go off to the right versus to the left. Right? Strange but true. Any thoughts about that one? Great. Let's just do one more, and then I got one for you all to try. How about, everything I've been saying today has been about horizontal asymptotes, but I hope you don't forget about vertical asymptotes also. Those are considerably easier to deal with. So here's a typical problem. Would be something like find any vertical and horizontal totes of this function. How about 5x squared, square root of 5x squared plus 7x over 10x plus 20. All right? Find any vertical or horizontal asymptotes. To find the horizontals, you do that stuff that we were just doing. The limit as x goes to infinity, and also the limit as x goes to minus infinity. Maybe they'll be the same answer, maybe they're different. Since I see a square root sign here, actually I expect them to be different, because I expect when I go to minus infinity, you have to insert that extra minus sign. What about vertical asymptotes? Does anybody remember how to find vertical asymptotes? It's actually quite a bit easier. How do you find a vertical asymptote? Let's do that first, just because it's easier. Vert, tote. Do you remember? The vertical asymptote is caused by a 0 in the denominator of your function. And so to find the vertical asymptotes, all you got to do is find when the denominator is 0. In this example, I think you can just kind of eyeball it, but in general, you would set the denominator equal to 0 and solve for x, right? In this case, I can tell that if x is negative 2, that makes the denominator 0. But if you want to work it out, it would look like this, right? And then solve it for x. 10x equals minus 20, x equals minus 2. So this is a vertical asymptote at x equal minus 2. On a picture, it would be back here. Right? And then what about the horizontal? For that, you got to do that stuff we were just doing about limit as x goes to infinity and also limit as x goes to minus infinity. And be careful with the signs of any square root stuff. So let's do the horizontal asymptotes. Totes. There could be one or more of both parts. Actually, there can only be at most 2 horizontal asymptotes. There can be many, many vertical asymptotes. So I'm going to do lim x goes to infinity, first of all, and my function is here. The numerator is totally irrelevant for the vertical asymptotes. I don't know about totally irrelevant, but it is in this problem at least. What do you think? Biggest power of x, I got to divide out by something. What should it be in this case? X to the 1, X to the 2, X to the, I see some fingers. X to the 1 is what you want. I see X to the 2 on the top, but it's inside of a square root sign, which means it only counts as a 1. So I'm going to divide by X. That means we get 1 over X. Would you mind if I just shove it inside the square root? Once you do enough of these, you really get, I hope that you begin to feel comfortable skipping a few steps here and there. Right? I'm dividing by X, but when it goes into the square root up top, it becomes an X squared. On the bottom, it's 10X over X plus 20 over X. All right? Simplify what you can, and then most of these things are going to become zeros when I do this limit. Up top, 5, this is just square root of 5 in there, and then plus 7 over X remains. And on the bottom, it's going to be 10 here, and then plus 20 over X. And then when I take the limit, these two guys become zeros. And I get root 5 over 10 is my answer. Whatever that number is. That's less than 1, isn't it? Root 5 over 10. Okay? So that's one horizontal asymptote. To the right, it goes to root 5 over 10. What about to the left? We also need to consider that one. X going to minus infinity, and it's going to be same function. Right? And we, do the same thing. Only this time we have to remember to insert the extra minus sign when we do the trick. So I am again dividing by X. This time the top picks up an extra minus sign. Minus root 5x squared over x squared plus 7x over x squared over 10x over x plus 20 over x. This all cancels out to negative 5 over 10. Negative root 5 over 10. Okay. All right. Any questions about that one? Thoughts? Desires? Yeah. It looks... So the true graph of this, I believe, I didn't graph this one myself, but the vertical asymptote is at -2. And then we said the asymptote to the right, horizontal, is root 5 over 10, which let's just say is there. Whatever that number is. And then it goes like this. So I believe the graph looks something like that. I'm not sure if that's what you're asking.
Yeah, so that's what we're going to use that. Like when we do the vertical asymptote, the horizontal asymptote change is at the vertical.
Yeah. I mean, so when you draw a horizontal asymptote, I draw it like as this dotted line going all the way across the picture, but really it only matters sort of all the way over to the right, you know? In terms of drawing the picture, all I mean when I say it has a horizontal is just that when you go off the far right side of the picture, it approaches this value. What happens in here is kind of anything goes. So it is possible, I don't think it happens in this example, but it is possible, for instance, for this line to cross over the asymptote back here, right? And it could even cross over here somewhere. It's just eventually has to approach that value. Yeah. It's probably too long of an answer to a simple question. Let's try. I got one for you all to try. Same question. You find the horizontal and any asymptotes, any horizontal or vertical asymptotes. 3x plus square root 5x plus x squared over x minus 5. See what you think. The vertical is easier. in my opinion. I'm going to start my answer slowly here. right, let's discuss these. This is my, so first of all, the vertical asymptote is x equal 5. That's, you just look at what makes the denominator 0. And that's easy in this example. For the horizontal, going to infinity, this is the first sort of important step. I'm dividing everything through by x, and inside the square root, it means dividing by x squared. And then most of these guys become zeros. I believe the only thing that remains after canceling will be the 3 plus 0 plus 1, like that. And then 1 down here minus 0, right? And then what is that? Up top, 3 plus square root of 1. That's 3 plus 1, which is 4 over 1. 4, right? So the horizontal asymptote to the right is 4. I hope you got 4. Easy to mess up little bitty bits in there sometimes, but that's what it ought to be. And then to the minus, limit as x goes to minus infinity. What's the difference? The difference is right here, when you move the 1 over x into this square root, it turns this sign into a negative. And so the appropriate sort of parallel step to that one that I wrote is this. All right, this is the, this got worse, trying to make a nice radical sign, and then it's all right. I made the square root part negative though. That's because the x is going to negative infinity. And like I always say, when you push that thing into the square root, if it's negative, the thing you're pushing into it, you have to flip the sign on the outside. Okay, anyway, again, most of this stuff becomes zeros, or it's just like before. But it becomes 3, this time minus root 1 over 1. And we've got 2 as the answer. All right, so these are our 2 horizontal asymptotes. To the right, it's a 4. To the left, it's a 2. I hope that's what you got. As I was walking around, some people asked me, like, hey, I learned some kind of cute trick in high school about, like, if the powers on the bottom is bigger, then you get 0. If the power on the top is bigger, then there's no limit. If the powers are equal, you get some kind of ratio of coefficients. If you learn such a trick, that's totally fine. If you want to do it that way, that'll save you some steps at the cost of you have to memorize what is kind of a slightly complicated trick. It's not complicated to do. You just have to remember. But yeah, that same reasoning that I just said does not exactly apply to this kind of situation. You have to change your attitude slightly about what exactly the highest power means. But anyway, you want to work that out if you learn some trick. That's fine with me. All right. Any other thoughts about this? Great. Just one more thing to say on the topic of limits at infinity. And then we'll move on to the next section, which is still very much related to this business. This is something I mentioned last time, is limit at infinity. This means, is like when I say lim x goes to infinity. That's called a limit at infinity. There is also something called infinite limit. An infinite limit. This means more like, this is like something like lim x goes to 0 of 1 over x squared equals infinity. All right? That's called an infinite limit, when the limit actually equals infinity. That's a totally different kind of thing. Usually, actually, this indicates a vertical asymptote, whereas this is talking about a horizontal asymptote. This says that as the x's approach a specific number, their y values go up forever, which is typically that's what you imagine when you think of a vertical asymptote, right? There's also a thing. This sounds like a sort of silly phrase, but there is such a thing as an infinite limit at infinity. How do you like that? This is like both scenarios. An infinite limit at infinity. This sounds much more complicated than it really is. This would look something like What is the limit as x goes to infinity of x squared plus 3? And the answer is, anyone want to say? As the x goes to infinity, so you have to imagine x is becoming infinite in this case. And what is this approach? Here's a hint. This is an example of an infinite limit at infinity. You want to imagine the x is going to infinity here. So the x is increasing forever. What is this actually, the limit equal? It equals infinity, yeah. That's why it's called an infinite limit, because it equals infinity. And it's at infinity because of this thing down here. The x is going to infinity. This is an example of an infinite limit at infinity, all right? It's because we have the infinity here and also here, right? That's what an infinite limit at infinity means. It means the x is approaching infinity and also the limit itself is infinite, all right? These ones, they are a little tricky in the sense that there's not like a standard method that you can just remember how to do to find the value of these kinds of limits. For example, what is the lim as x goes to minus infinity of x squared plus 3? This is also infinity. Even though x is negative infinity, because we square it, it ends up being positive in the end. And so this is also equal to positive infinity. But something like lim x goes to minus infinity of x cubed plus 3, this is negative infinity, because here it's because x is becoming super duper negative, and I cube it, and the cube of a negative is also a negative, all right? So I'm going to say these, you usually have to think it through. There isn't a standard sort of cute memorizable trick to do these. You really have to look at the formula and think about, you know, in this example, the thoughts that I have is, what's going to happen here if x is a super big number and negative? And the answer is, I get a super big negative number as the answer. But the fact that it's negative has to do with this third power here, right? You have to just kind of think it through. So I wanted to let's just do a few very simple examples. We're not going to get really into this very deeply, other than just to say this is what it is, and it's, they're, you know, complicated from time to time. How about this? What about lim x goes to infinity of x to the 5? This is infinity. If I have a super big number and I take it to the 5th power, it's just going to give me a super duper big number, right? If the x is going to minus infinity of x to the 5, this is going to be minus infinity. That's because if I have a big negative number and take a 5th power, I again get a big negative number. So in a very simple case like this, you can say there is a rule. If the exponent is even, then you'll get a positive infinity. If the exponent is odd, you'll get a negative infinity there. Although that only applies to this very specific situation. Here's another less clear example. What is lim x goes to infinity of x squared minus x? So here's an example where trying to use some rules might lead you astray, whereas you just have to sort of think it through. Using some kind of cute rule might suggest that this is something like infinity minus infinity, right? Like the x squared, if x is becoming really big, then the x squared is becoming really big, and also the x is becoming really big. And what is infinity minus infinity? Correct answer is like, that's not really a thing. Like, infinity isn't a number. You don't typically add or subtract infinities from each other. You certainly should not say the answer here is 0 because the answer is not 0. Like, when x is super big, this doesn't look like 0, right? X squared minus x. You don't get 0 when you plug in like 1,000,000 for x here, right? So the answer is definitely not 0. I'm just going to say, don't do that. It's not 0, right? You have to think a little bit more about this. Actually, I feel like you should feel like if I were to plug in like x equals 1,000,000, I'm still going to get a really big answer here, right? It would be 1,000,000 squared minus 1,000,000. That minus 1,000,000 is not all that relevant compared to the 1,000,000 squared part, all right? Actually, the trick which is used in this example would be to factor, this is weird, but you can factor out of x, like that. And now I think it's obvious that this is just infinity, right? But you have to think this through. If x is a super big number, and I multiply x times x minus 1, the answer will be a super big number, right? That's all you gotta say. But it's not because it's like infinity times infinity minus 1 or whatever. You have to actually think about each function sort of as its own special case, and there aren't cute rules to remember about this. All right? And that is all I want to say about infinite limits at infinity. Anybody got any questions about that? Basically, I want to say it's complicated. We're not going to really do it very often. All right? Excellent. Continuing our general theme of asymptotes, I would like to try one example of curve sketching with asymptotes. You know, we spent a day and a half or so last week doing sketching curves. I just wanted to revisit that for one example, sketching with asymptotes. All right? It turns out the asymptotes actually can help you to draw the picture sometimes. So I will just start off by saying we should, or we need to look for asymptotes when we see denominators, right? When you see a denominator. If your function has a denominator in it, that means it probably has a vertical asymptote where the denominator is 0. And it might have a horizontal asymptote when you do limit as x goes to infinity, or x goes to minus infinity. These are not all that different from the other curve sketching things, but I wanted to do one example at least, and then we will, this will be it for our curve sketching. So let's just try an example here. I would like to sketch the curve of, how about f of x equals 2x squared plus 1 over x squared minus 1. So when I see that, it immediately occurs to me that I need to worry about asymptotes, just because I see the denominator there, and I can see already that it is possible that that denominator might be 0. And also, I mean, I can see the numerator, so you should expect some horizontal asymptotes as well. Let's work it out. So I'm just going to start with the totes. Oh, I put the apostrophe at the end. Should be over here. The totes. I left out the asymptote. All right, there's the vertical and the horizontal. Okay, the vertical is typically easier. These are numbers which make the denominator equal to 0. If you can't just eyeball it, you can set up an equation like this and then solve for x. In this case, I would say that, and then take a square root. X equals plus or minus 1. I hope you get both of them there. It's plus 1 and minus 1, which can make that denominator equal to 0. So I have two vertical asymptotes. How about horizontal? Horizontal asymptotes would be the limit as x goes to infinity, which is all that stuff that we were saying before. So I'm going to go lim x goes to infinity of this function, 2x squared plus 1 over x squared minus 1. There's no square roots involved here, so I'm just going to divide through by the highest power of x that you see there. You don't have to do any adjustments for square roots or anything like that. So I'm going to divide out by x squared. 2x squared over x squared plus 1 over x squared over x squared over x squared minus 1 over x squared. The two guys on the end will become zeros, and the other ones, I believe I'm going to get 2 over 1, which is 2. All right? That's what happens. If you remembered if you memorized some trick in high school, it would have said, since I have the same degrees on the top and the bottom, the ratio of the coefficients is 2 over 1, which is 2 over 1. Right? That's fine with me if you want to think of it that way. Okay, that's the horizontal asymptote as I go to the right, going to infinity. What about going to the left? It's going to be the same. The only time it's different is when you have a square root and you have to do that weird trick with the extra minus signs. But I'm just going to say, just for the sake of completeness, I'll write it down. It's the same, also 2. All right. No difference going plus infinity versus minus infinity unless there are square roots with that weird technicality that you have to deal with. Okay, so the picture, maybe would you mind if I just start drawing my picture right away? It has vertical asymptotes at +1 and -1. That's here and here. +1 and -1. And then a horizontal asymptote at 2. Let's say that's here. All right. So this is my picture so far. How do I do the rest of it? The rest of it I'm going to do just the way that we did the curve sketching problems from, that we did last week. So I'm going to start by finding the critical numbers. That is where the derivative, first derivative is 0 or does not exist. And then make a little chart of the increasings, decreasings. And actually, it turns out in this example, you don't even need to find the concavity. Once you find the increasing, decreasing, it becomes clear what the picture has to look like. So let's do the critical numbers. This would be f prime. I set f prime equal to 0, or I say when f prime does not exist. Now, this is going to be a little bit of work to find this derivative. I'm just writing the original function again. 2x squared plus 1 over x squared minus 1, and then f prime. I'm going to do the quotient rule, right? It's the bottom times the derivative of the top. Derivative of the top is 4x minus the top, 2x times the derivative of the bottom is 2x. All of this over the bottom squared. That's the derivative. I want to set this equal to 0 and also say when this does not exist. Now, I'm going to let's simplify a little bit before doing that stuff, just because it'll be worthwhile. Up top, to simplify, I would first distribute the 4x here, and then also distribute over here, and then add everything together on top. So distributing to the left gives me 4x cubed minus 4x, minus this guy distributing will be 4x cubed plus 2x over the same stuff. And we can subtract up top by combine the like terms. 4x cubed will cancel with a 4x cubed like that. And then we get negative 4x and then a negative 2x adds together. Negative 6x up top over x squared minus 1 squared on the bottom. All right. That's as simple as this is going to get. This is the first derivative. All right, that's the first derivative. I hope you got that. There's a lot of opportunity, unfortunately, to screw it up in the middle there, which totally screws your graph. But my only advice is do it right. Don't screw it up. I don't really have advice, but you just got to be careful. All right. Remember, I'm finding the critical numbers. That means set equal to 0, and also say where it does not exist. Okay, I'll set equal to 0. It says minus 6x over this business equals 0. How do we solve this? I would multiply the denominator across, and it's just going to multiply times 0 on the right side. So this, when I multiply the denominator across, looks like that, right? The denominator gets multiplied onto the 0 on the right, and it's just going to be 0. And so x equals 0, right? 0 divided by 6 is 0. Hope you got that. So this is a critical number when f prime of x is 0. And then also f prime does not exist. Again, we look at this and say, when could the denominator be 0? And it's actually the same two numbers. It's still plus or minus 1, right? X equals plus 1, x equals minus 1. The denominator is pretty much the same as it was the first time through. It's just squared now. All right, so we have three critical numbers. I'm going to make my little increasing and decreasing chart, right? These are the three critical numbers. Increasing, decreasing. And then, like I said, this is actually going to be enough in this example to let us draw the picture. We have a minus 1, a 0, and a plus 1. For the derivative, it's 0 in the middle there. It does not exist here and also here. All right. And I'm going to choose specific points to plug in and say the signs of the derivative. Is it positive or is it negative? And the thing I'm looking at throughout is that thing in the box. Negative 6x over that thing squared. To help us out with the signs, I hope you will agree with me that the denominator of this fraction is always positive, right? It's something squared. So when I'm plugging numbers in, you don't really need to worry too much about the denominator. It's always positive. So let's start off with negative 2 all the way to the left. It says negative 6 times negative 2 over some business squared. This is going to be positive over positive, so that is positive. Right? In the next region, between minus 1 and 0, I guess I have to use negative a half. I think it's going to be the same situation, though. 6 times negative a half over something squared is, again, positive over positive. So it's a positive in that region. And then on the right side, I'm going to use positive a half and positive 2. I think you can see what's going to happen. When I use positive a half instead of negative a half, I get minus over minus. So when I do f prime of a half, minus 6 times a half over something positive, which is negative over positive, which is negative. So that's a negative, and similarly with the other one, f prime of 2 is negative 6 times 2 over something squared. This is negative, negative, all right? So I see, this is increasing, decreasing, right? So I see increasing, and then increasing, and then decreasing, and then decreasing. So I'm going to try and draw my picture. I'm gonna scroll away from this little chart here. When I draw my picture here, what I want to see is increasing over here, increasing here, decreasing, decreasing. Oh, one more thing. You got to plot the critical numbers with their y values, right? I had 0, plus 1, and minus 1. Now, plus 1 and minus 1 don't get y values because those are the asymptotes. They don't actually represent points on the curve. So the only one that really matters, sorry, I'll squeeze this in here. Critical numbers y values will be f of 0, right? The critical number 0, that really is a real point on the graph. The other two, plus 1, minus 1, they don't represent actual points on the graph because those are the asymptotes. How do you find the y value? I hope you remember. You plug into the original function, f of 0. The original function, I don't see, actually it's this, right? No? This one that I see here. That is the original function. So I'm going to plug in 0 to this. I'm going to look all the way back. It's that, right? When you plug 0 for x, you get 2 times 0 squared plus 1 over 2 times 0 squared, not 2, sorry. On the bottom, it's just 0 squared minus 1. This is 1 over negative 1. Negative 1, all right? So, I'm really ready now. Right down here is my critical number. Plotted it, that big red dot. All right? And this is a critical number at which the derivative is 0. So when the graph goes through that point, its derivative, it's going to be a horizontal slope when it goes through that point. Okay, can we draw the graph in here? Just think about connecting the dot. Well, there are no, usually I say connect the dots. There are no dots to connect there. But I have this dot here. Think about what happens as I proceed to the right from that dot. It's going to go up or down. What do you say? Just give me the thumbs if you want. As I proceed to the right here, should it go up like that or down like that? You can tell based on the work that we've already done. I see some thumbs out there. I already said it's decreasing in this region, right? That means it goes down. And in fact, the asymptote will help you out. You know it has to respect the asymptote. It has to do that, right? It goes down and approaches the asymptote. So it's kind of a lumpy curve there. I'm trying to do better. Oh yeah, I like that better. All right, it's decreasing, so it has to go down and approach the asymptote. There's really only one thing that it could look like. Okay, what about to the left of that point? Again, it has to respect the asymptote. So really, there's only two choices, right? To respect this vertical asymptote, it either has to do that or it has to do that. And which one is it? Well, I said before, it's increasing in this region. Yeah, make sure you're thinking properly. Is it the one that is going up top or down below? It's the down below one. Yeah, it's increasing. Remember, increasing means as you move from left to right, it's going up. That means it's this one, right? This one actually is decreasing as you move from left to right. So not that one up there. Is that one down there? This one. Right? It's increasing up to this point, increases up to that point, and then afterwards it decreases down from that point. All right? And then what about over here and over here? All right, we've got to draw those in. You don't get any points at all over there, which actually is not such a big deal. Over here, it has to be decreasing, and it has to respect both asymptotes, the vertical asymptote and also the horizontal asymptote. What that means is, how about, let's draw in, what could it possibly be? Well, to respect the vertical asymptote, either it comes down, sort of from heaven, or like up from hell, right? And it has to approach the horizontal asymptote also, which means sort of this one, which came down from heaven, actually, eventually it would have to do that. Or this one would have to do that, right? And those are really the only two options that we have in this case. If it's going to respect both asymptotes, it has to fit in one of those two ways. And which one is it? It has to be decreasing, which means as you move left to right on the picture, it's going down. That means it's got to be this one, because this one down here is increasing. So it's that one. All right? Maybe I'll give you a moment. Can you fill in the last bit? Would be on this side. Where does it have to go? It has to be increasing as you move left to right, and it has to appreciate, or it has to respect those two asymptotes, the horizontal and the vertical. Maybe you've already scribbled it in. Give you a moment to think about it. Is that a long enough moment? You got two choices, right? To fit both asymptotes, it's either going to be this here or this here. You might wonder, like, what about something like that? Isn't that possible? Well, the answer is kind of yes, that is possible. Like, you might be concerned about, am I allowed to drive through the asymptote? You are actually allowed to drive through the horizontal asymptote, because remember, horizontal asymptote, it only means where it ends up when you go way out to the left. All right, so in theory, this is possible, this is allowable, but the reason you know it doesn't happen in this function is because that would have been a critical number in such a case. And we've already found there are no other critical numbers. So it's impossible for your curve to ever have one of those kind of wobblies in it, which means really there are only two options, one of those two. And you have to choose the one which is increasing. That is, as I move from left to right, it goes up. That means it's this one, not that one down there. It's that one. All right? I'm going to do it nicely. A nice, smooth line there. All right? This is my final answer. The asymptotes, they actually help you to decide where the curve has to go. So don't feel like the asymptotes are your enemy. They can be your dearest friend sometimes. All right? This is all I wanted to say about the curve sketching. We got 5 minutes. I think that's enough to start the next section. Can you believe it? All right, scrolling past this business. Our next section, I wanted to start off with a very easy example. So this will be a good 5-minute introduction to the next section. This has nothing to do with curve sketching. I want to talk about optimization problems. This is the next section in the book. Optimization problems. These are all going to be word problems which have the format of, so they're all problems like find the value of whatever which maximizes whatever, I'll say, or minimizes. This is a huge category of the applications of calculus in the real world. Calculus is very useful for solving optimization problems, which is, it means I'll give you some sort of scenario and I ask you to figure out how do I get the most of something, or how do I make the least of something. In the real world, this would be like, how do I make the most profit, or have the least expenses, or when I shoot the rocket, what's the maximum height that it achieves, or something like that. And any kind of question about maximum or minimum values of something or other is, can be phrased in terms of this optimization framework. So let's just try a very simple example, and then, like I said, we'll do more complicated ones tomorrow. Let's say when I make, this is my old maple syrup jars. Let's say when I make X jars of maple syrup, my profits obey this formula. This is a totally made up formula. F of x equals minus 6 minus x squared plus 40x. All right? X represents how many jars of maple syrup I make, and then I sell them to my friends and family. And this is how much money I get after selling X jars. Okay? And I would like to ask, let's say I can make anywhere from 0 to 100 jars. How many should I make? And the implied question is, in order to maximize the profits. That's what, I'm a good American, so I want to maximize my profits. How many should I make to maximize profit? All right? And our basic approach here is to think of this as an absolute extremum problem. I want to find the absolute maximum of the profit, right? So this is an absolute extrema problem. I want to find the x which makes that function that you see at the top have its absolute maximum. That's the most possible profit. Remember, an absolute extrema problem always requires a closed interval, right? You have a certain function. I want to find out what's the highest value it ever achieves. And you always need a closed interval because, as we remember from the extreme value theorem, it says that the minimum and the maximum, they either occur at critical numbers or at the interval endpoint. So we need interval endpoints here. This is an absolute extremum problem, and the interval of x values is hopefully in there somewhere. I said, like, what's the smallest possible x value and what's the greatest possible x value? So that's what that 0 to 100 is. So the interval of x values is 0 to 100. All right? And from there, you just do the usual absolute maximum thing. That is, I'll just say it in words, we don't have time to do it now, but you would find the critical numbers. The absolute maximum occurs either at the critical numbers or at the interval endpoints. You plug in the critical numbers, you plug in the interval endpoints, and you just see whichever one is the biggest. We'll go through the details of this. This one is not hard, but we're out of time.